Okay, let's start with these two examples. So what I have here is a product of two expressions. With u-sub, you always want to be looking at a product. And then I see this x squared up here, and I recognize that its derivative, 2x, also appears out here. So one of the expressions in this product is the derivative of a part of the other. So what I'm going to do is let u equal x squared, so that du is going to be 2x dx. That's how I like to write it. Instead of du dx equals 2x, du equals 2x dx, then I'm looking to replace this with just the differential du. I need to change my bounds. When x equals 3, u is 3 squared, so u is 9. When x is 6, then u is 36. So 6 squared is 36. Okay, and that's all the pieces I need to convert this integral from one with respect to x to this new variable u. We will say that this is going to be the integral from 9 to 36 of e to the u. So this expression here gets replaced with e to the u, and then the 2x dx is going to get replaced with du, like that. Now the idea with u-substitution is that after doing the substitution, it's something easier to integrate. So the antiderivative of e to the u is e to the u, and then my bounds for u go from 9 to 36. So with the fundamental theorem of calculus, we conclude that this integral is going to be e to the 36, I started to write 36, e to the 36 minus e to the 9, which is some really large number. The second integrand that we have here on the right is written as a quotient, but we can take this and rewrite it so that it looks like the product of two expressions. I'll say this is the definite integral from 0 to pi over 2 of 1 over the square root of sine of x plus 5 times cosine of x dx. Okay. Looking at this, again, you want to recognize that one of the terms looks like the derivative of something that belongs to the other term. So in particular, cosine of x looks like the derivative of sine of x. In fact, it is the derivative of sine of x. So you might start to set this up by saying let u equal sine of x. However, we could actually do better. I recommend trying to take the biggest u that you possibly can, so try to absorb as many terms as you can. While the derivative of sine is cosine, the derivative of sine of x plus 5 is also cosine, because the plus 5 isn't going to affect your derivative, it's just a constant. So I'm going to let u be sine of x plus 5, so that du is cosine of x plus 0 dx, so cosine of x dx. And then we see that expression here. Our integral is now going to be 1 over the square root of u. So sine of x plus 5 got replaced with u. And then cosine of x dx is going to get replaced with du. So this is a much simpler looking integral to compute. We still have to change the bounds. When x is 0, I plug 0 in for x in my definition of u here. We get u is sine of 0 plus 5. Since sine of 0 is 0 itself, that's u equals 5. So the new lower bound is 5. When x is pi over 2, u is going to be sine of pi over 2 plus 5. Sine of pi over 2 is 1, so the upper bound for u is 6. Okay, so that's the new integral. Anti-differentiating this is now not too bad. 1 over the square root of u is the same thing as u to the negative 1/2 power. So using the power rule to anti-differentiate this, we can say that's going to be u to the positive 1/2. And then 1/2 drops down, minus 1, that gives me negative 1/2, but I need to multiply by 2. Okay, so that should be the antiderivative. And then we plug in 5 and 6. And we get 2 square root of 6 minus 2 square root of 5. Like that. Okay, let's do a couple more examples. So example 3 here on the left, we have the product of 4x and cosine x squared inside of this integral. This is an indefinite integral, so I'll show you how to handle that. So I've got a product here. That's one reason why I think u-substitution. So with u-substitution, you always want to be looking at the product of two expressions. Then I don't have like a perfect match between a function and its derivative, but I have something which is close enough, up to a scalar multiple. So in particular, inside this cosine, I'm taking x squared. The derivative of x squared is 2x. That's not exactly what I have out here with this 4x, but it's close enough. As long as it's a multiple of the derivative, that's good enough. So what I'm going to say is u is x squared, then du will be 2x dx. And then what you can do, since it's just off by a multiple, is figure out what you can multiply both sides of this equality by in order to make it a perfect match. So in particular, if I multiply both sides by 2, then I will pick up a 4x dx, and that's going to allow me to make a perfect replacement in my original integral. So 2 du is 4x dx. Okay, so now we can say that this indefinite integral is going to be cosine of u. 4x dx gets replaced with du. Gets replaced with 2 du. Okay, so this is the indefinite integral of 2 cosine of u du. Let's go ahead and anti-differentiate. That's going to be 2 sine of u plus c. You don't want to leave it here, because we were not asked to compute something in terms of u. Our original integral was in terms of x, and our final answer needs to be in terms of x. Otherwise, we're saying the antiderivative of 4x cosine x squared is 2 sine u plus c, and that doesn't make any sense. So what I need to do is replace u with the appropriate expression in terms of x. So the antiderivative of 4x cosine x squared is 2 sine of x squared plus a constant. Okay. So you can use the u-substitution on a definite or indefinite integral. When it's an indefinite integral, you have an extra step here where you need to convert from your new variable u back to your old variable x. Okay, let's look at this example 4. Again, it's a product. So I've got x out front times the square root. I see an x squared in here, I see an x there. Since the derivative of x squared is 2x, and that's just off by a multiple from x, then that means this is a u-sub problem. All right, I could say u is x squared, I could say u is 3x squared, or I could say u is 3x squared plus 1, and that's the one I'm going to pick because I usually want my u to be as big as possible. So let u be the inside of the square root, so 3x squared plus 1. Then du will be 6x, and that's it, 6x dx. So x dx is just du times 1/6. Let me just write 1 over 6, cancel that out. Okay, so the integral in terms of u is going to be 1 over 6 times the square root of u du. Okay, so our whole square root expression got replaced with square root of u. X dx got replaced with 1/6 du. The only thing I have to do now is change my bounds. So when x was 0, the lower bound, u was 3 times 0 plus 1. The lower bound is 1. When x was 4, u was 4 squared is 16 times 3 is 48, 49. Like that. Okay, let's anti-differentiate. So we're going to have 1/6 u to the 3/2, and then if that came down, I would need to multiply it by 2/3 to cancel out. So we have this as our antiderivative, and then the bounds for u go from 1 to 49. Okay, so that looks like that. Let's keep going. Just write it here. So that's going to be 1/9. U to the 3/2 power is the square root of u cubed, which is going to be the square root of 49 cubed. I'll write it this way first, minus the square root of 1 cubed. (49 cubed, if you took the square root, that's going to be 49 times the square root of 49, which is 49 times 7, which is a little beyond my mental math at this moment, so I'm just going to write 49 times 7, and then minus 1, and we'll leave it there. Okay, so in both of these examples of u substitution, what I wanted to point out was that sometimes you don't have a perfect match between the derivative of u and what you recognize as similar to the derivative in your integral, but if it's off by a multiple, that's fine. You just make a little adjustment, and you can still make your replacement. Okay, let's finish with these two examples. For example number 5, we are taking the definite integral from 1 to e of natural log of x plus 1 divided by 3x and then dx. Let me rewrite this as the definite integral from 1 to e of natural log of x plus 1 times 1 over 3x dx. We see here a natural log of x, and then I also see a 1 over x, which is the derivative of natural log of x. Anytime you have natural log in an integrand, you want to use some kind of technique of integration, and if you have anything that looks like 1 over x, you might be thinking u substitution. So what I'm going to start by doing is letting u equal natural log of x. That way du is 1 over x dx. And that's okay, but I recommend making your u as big as possible so that the du will still work. And in this case, what I mean by that is if I add this 1 to my u, I don't affect du at all. So we can allow u to be natural log of x plus 1. Du is still going to be 1 over x dx. And that's very good, because that's what we see right here. If I want to take care of that 3 at the same time, I can divide both sides of this by a third, so that we can take 1 over 3x dx, this whole expression here, and replace it by 1/3 du. All right, go ahead and set up this integral. Change your bounds at the same time. So the bounds from 1 to e were with respect to x. We need to have bounds for u. So for that, you need to remember what natural log of 1 and natural log of e are. And then at the end, the resulting integral is quite simple to do. So I'll work that out for you in just a minute. Okay, let's see if we get the same answer. The bounds for u are going to go from natural log of 1 plus 1, which is 1, to natural log of e plus 1, which is 2. Let me say that a little bit more slowly. Natural log of 1 is 0. That's something that you should know. And another thing you should know is natural log of e is 1. So when I take x and let it equal 1, u becomes 0 plus 1. When I take x and let it equal e, u is natural log of e plus 1. So that's how I got 1 to 2. Then we're going to have u times 1/3 du. Let me write this as just 1/3 u du. Okay. Then we antidifferentiate, and we'll have 1/3 times the antiderivative of u, which is 1/2 u squared, from 1 to 2. So we get 1/6 times 4 minus, 1/6 times 4 minus 1, and that is 1/2. All right. So here, the main message was, when you see natural log, you see 1 over x, u substitution might be the correct approach. Let's finish with number 6 now, which is pretty challenging. This is one where if you've never seen this kind of integral before, you might not recognize how to solve it as a u substitution problem. And there's also a way to think about trying to use u substitution which is incorrect. So let me start there. If you look at these expressions in your integrand, I see x cubed and I see an x squared. So it's tempting to think, well, what if u was x cubed? So that du was 3x squared. And you know, that's reasonable because you have those two expressions here, and we know that x squared looks kind of like the derivative of x cubed. This is not correct, though, because you never want your du expression to be inside of a square root, raised to a power, inside of a natural log, in a denominator, anything like that. It really needs to be standalone, kind of like over here. After I rewrote this integral, I had the whole expression just by itself, not inside of another function. So you do not want to take this and try to replace it with something to do with du, because that's just not going to be correct. It's inside of a square root. So instead, what we're going to do is let u be x squared plus 4. And again, this is not obvious if you haven't seen it before, but let me show this to you in case you run into this again. You'll know what to do. If u is x squared plus 4, du is 2x dx. Okay, let's compare that to what we have left in our integral. I have dx here, and then x cubed I could write as x squared times x. So that means that my x dx look like the du expression up to a constant multiple. What I've been left with is this x squared term right here, but that looks like u. In particular, if u is x squared plus 4, u minus 4 is x squared. And then that would take care of the remaining term that I haven't already identified. So let's go ahead now and make all our replacements. This is an indefinite integral, so I'm not going to need to change bounds, but after I anti-differentiate, I will need to revert back to the original variable x. Okay, so where I had x cubed, I'm going to think of that as x squared, so that's u minus 4. X squared times x dx. X dx is 1/2 du. Let me write 1/2 du like that, and then we'll put the square root in the middle. Square root of x squared plus 4 is going to be square root of u. Okay, so kind of stretched it out a little bit too much. So let me rewrite this as 1/2 times the indefinite integral of u to the 3/2 power minus 4u to the 1/2 power. I'll step back and see if that looks correct. So go ahead and check what I've done here. Okay, now we're going to anti-differentiate. So we have 1/2 times u to the 3/2 power. The antiderivative of that is going to be u to the 5/2 times 2/5. And then minus 4 times u to the 3/2 times 2/3. That's the antiderivative with respect to u, but our integral was with respect to x. So we need to convert from u back to x now using the relationship that we already have between them. So if I can squeeze it down here one more time, we have 1/2 times 2/5. Where I have u, I'm going to write x squared plus 4 to the 5/2 power minus 8/3 times x squared plus 4 to the 3/2. And then these were indefinite integrals, so let me go ahead and add my constant of integration. All right, so this is a tricky one, but it can still be done with u-substitution. So here, you know, it's not easy to recognize that x cubed is going to have the du expression built into it as well as something to do with u, but you can sometimes encounter these where u doesn't happen only once in your integrand, you're actually going to use it several times. So we found u here, and then also where we had x squared, we replaced that with u minus 4. So I'll be on the lookout for that. You know, if you're stuck on an integral, it still could be a u substitution. It just might be kind of one level higher than your standard u substitutions.